The engine of deep learning optimization algorithms. Deep learning, a powerful subfield of artificial intelligence, focuses on training artificial neural networks to learn from data. These networks, inspired by the human brain, excel at tasks like image recognition, natural language processing, and more. At the heart of training, these networks lies the crucial role of optimization algorithms. These algorithms act as guides, steering the network's learning process towards finding the best possible parameters, which are the weights and biases. The journey of optimizing a neural network involves minimizing a loss function, which measures the discrepancy between the network's predictions and the actual target values. Imagine a vast, intricate landscape with hills and valleys. The lowest point in this landscape represents the optimal solution, where the loss function is minimized. Optimization algorithms help us navigate this landscape, starting from an initial point and iteratively updating the network's parameters to descend towards the minimum. The choice of optimization algorithms significantly impacts the efficiency and effectiveness of the training process. A well-suited optimization algorithm can accelerate training, leading to faster convergence and improved model performance. Conversely, a poorly chosen algorithm may result in slow convergence or even prevent the network from reaching a satisfactory solution. Gradient descent, taking small steps towards the solution. Gradient descent, a fundamental optimization algorithm, forms the basis for many advanced optimization techniques in deep learning. It follows a simple yet intuitive principle, iteratively adjusting the network's parameters in the opposite direction of the gradient of the loss function. The gradient, a vector of partial derivatives, indicates the direction of the steepest descent of the loss function. By taking steps proportional to the negative gradient, we move towards the minimum. Imagine a hiker trying to find the bottom of a valley. They can use gradient descent by taking small steps downhill. The direction of each step is determined by the slope of the terrain at their current location. Similarly, gradient descent adjusts the network's parameters based on the gradient of the loss function, gradually moving towards the minimum. However, gradient descent has its limitations. It can get stuck in local minima, which are low points in the loss landscape but not the global minimum. Additionally, it can be slow, especially when dealing with large datasets, as it requires calculating the gradient over the entire dataset in each iteration. Stochastic gradient descent, or SGD, addresses the computational inefficiency of gradient descent by introducing an element of randomness. Instead of calculating the gradient on the entire dataset, SGD computes it on a small, randomly selected subset called a mini-batch. This significantly reduces the computational cost per iteration, making it much faster, especially for large datasets. Imagine our hiker now navigating a maze instead of a valley. Instead of surveying the entire maze at each step, they randomly choose a path and follow it for a short distance before reassessing. Similarly, SGD updates the parameters based on the gradient of a mini-batch, introducing noise but ultimately leading to faster convergence. While SGD's randomness introduces noise in the parameter updates, it also helps it escape local minima. The noise acts as a form of exploration, allowing SGD to jump out of shallow valleys and potentially find the global minimum. This stochasticity makes SGD a powerful optimization algorithm for deep learning. While SGD is a significant improvement over gradient descent, researchers have developed even more sophisticated optimization algorithms to further enhance the training process. These advanced optimizers address some of SGD's limitations and often lead to faster convergence and improved model performance. AdaGrad adapts the learning rate for each parameter individually, based on the historical gradient information. It performs larger updates for infrequent parameters and smaller updates for frequent ones. This adaptive learning rate strategy proves particularly useful for sparse data. RMSprop, short for root mean square propagation, tackles the problem of diminishing learning rates often encountered in SGD. It maintains a moving average of squared gradients and divides the learning rate by the square root of this average. This normalization technique prevents the learning rate from becoming too small over time. ADAM, short for adaptive moment estimation, combines the benefits of both AdaGrad and RMSprop. It maintains moving averages of both the gradient and the squared gradient, incorporating momentum into the parameter updates. This momentum helps accelerate SGD in the relevant direction, leading to faster convergence.